Hello and welcome one and all. In this video, we will discuss systems of equations, what they are, how to solve them, and then some practical applications in the end. This topic is extremely important and really a fundamental math skill and will help you in many problems such as SAT problems, physics problems, and beyond. Although this video is tailored for solving SAT-like problems, we will go through physics and word problems once the fundamental skill is established. First, a quick review. You should know this, so I'll be quick about it. An equation states that two things are equals, characterized by an equal sign. The equations we'll be looking at will have what are called unknowns. Our job is to find the numerical value of these unknowns. When we do so, we must make sure that the equality is maintained. But what if there are several unknowns? Then we must use a system of equations. In this first example, let's give ourselves two equations and two unknowns. Alright, let's try and solve this system of two equations and two unknowns. Let's first take our first equation, and let's create what is called an expression of y in terms of x. What does that mean? That means that we want y to be on one side of the equality and everything else to be on the other side. How do we do that? Well, for y to be on one side, we need to subtract by 3x on both sides. Make sense? Good. Now we have our expression of y in terms of x. Y is equal to 25 minus 3x. And what does this mean? This means that if we were to take our second equation, we could replace y with our newfound expression, which is 25 minus 3x, and the equality would still be maintained. Let's do exactly that. So 5x. This is our second equation, but again, we're plugging in the expression for y as a replacement for y. So negative 2, times y, which is 25 minus 3x, and this is equal to 5. Our equality on the two sides of the equation, the equality is still maintained because y is equal to 25 minus 3x. Let's keep going. Let's multiply each part of the parentheses by the negative 2. So this gets minus 50, and this minus minus is plus. So plus 6x. And let's make the x nice and red here as well, just for the sake of continuity and making this easy to see. Now, we want to solve. This time we only have x and numbers, so we can have a number value. We can assign a number value to x. Right? We can solve this equation. So let's do exactly that. Right? By adding 50 to both sides, we get 5x plus 6x is equal to 55. Let's make those x's red. 5x plus 6x is equal to 55. Now 5 plus 6 is 11. So 11x is equal to 55. We divide by 11 on both sides, and we get that x is equal to, not 55, x is equal to 5. And this is our answer for x. Now, again, if x is equal to 5, that means that x and 5 are the same thing. So, the same way we replaced the y in our second equation with 25 minus 3x, we can replace x with 5 in our expression of y in terms of x. And what does that look like? That looks like this. Y is equal to 25 minus 3, and then let's do this 5 in red, just so that it's clear that the x is the 5, right? The x has turned into the 5. So y is equal to 25 minus 15. So y is equal to 10. And now we have a numerical answer for both x and y. And if we were to plug these in our original expression, we would get 3 times 5 plus 10, which is equal to 25. And this is true. And if we were to do 5 times, again, the 5 minus 2 times 10, that is equal to 5. And so our equality, once we've gone through this whole thing, we can see that our equalities from our original equations still hold. Now this is extremely useful, and the way we solved this was by going through a pretty straightforward and pretty modular step-by-step. And I really want the people watching this to think about this in a step-by-step manner. So, our first step, do this in a nice new color. So let's pick yellow, since that's the default color for the highlighter. Our first job was to choose one of these two equations. I didn't have to choose the first one, but I chose to because it was the first one and it was easy, and I've designed the problem so that the first one, it makes it simpler to solve. So we take this first equation and we turn this first equation into our expression of x our expression of y in terms of x. So we have y on one side and what y is equal to on the other. And what y is equal to will have a purely numerical part and a part that is multiplied by x. And we will see this in other exercises as well. So we take our equation, turn it into an expression of y in terms of x, and then we use the fact that this y and this y are equal to each other to plug this in, and to plug our expression of y in terms of x as a replacement to the y in our second equation. Just like that. So we then, solve this equation until we get yet another expression. This time, it's an expression of x. Since we took out y is no longer present in this y is no longer present in this equation. We have substituted y out. That's why this is called the substitution method. And then we solve this, and we get an expression for x. And this expression is just a number, and that means that it's a job well done, basically. Once we have this number, right, once we have the value of x, we can go back and plug in this value into our expression of y in terms of x. Since all we needed to solve for what y is in this expression is the value of x. And now we have the value of x, so we can find y. And that's exactly what we do here. And then eventually we find it, and we have our answer. We have y, and we have x. And that is how you solve a system of equations. Let's do another example. Once again, let's go through our modular step-by-step process that we established in our previous example. Let's choose an equation. Once again, let's choose the first one. All right, let's this time find an expression for x in terms of y, just to mix it up. It doesn't really matter. So, regardless of which equation you start with or which variable you create the expression of first, you should always end up with the same end result. And let it be an exercise to the watcher, if they so wish, to redo all these examples, but mixing it up, choosing the other equation, and so on. All right. That being said, we now have our expression of x in terms of y. Now, let's plug it in. We have 12 times 1 plus y in blue. Let's make y blue here as well. 1 plus y over 2, which is equal to 5y still blue plus 8. Perfect. Let's multiply this 12. The 12 and 2 cancel to make 6 plus 6y is equal to 5y is blue plus 8 minus 5y on both sides. 6 plus y is equal to 8. Y is equal to 2. All right, let's plug in y is equal to 2 in our expression. And what do we get? We get that x is equal to 1 plus, let's make this blue, sorry. 1 plus 2 over 2. X is equal to 3 over 2, also known as x is equal to 1.5. Let's make those x's red for the easiest possible visual appearance and understanding. All right. I went through this example a bit quickly, but you should have gotten the gist of it by now. Let's again go step by step. We start with, let's go green. We start with these two equations. And we choose one. I chose the first one. Again, I didn't have to, but the first one looked like it would make the simplest expression, so I went for it. If you find yourself trying one and seeing that the expression that you get is hard to work with, you can always restart and try another equation or the expression in terms of the other variable and see if that lands you in a better spot. I obviously planned this all out beforehand, so I always end up in the easiest one as if it were magic. So we grab this, we choose our first one. Again, I chose x just because last time we did y. So we got our expression of x in terms of y. Plug that in right there. I've noticed there is no x in this. As soon as we reach this equation, there is no more x. There is only y. And one equation, one unknown. We know how to do that. Pretty straightforward. We get a numerical answer. Plug our numerical answer into this expression, and we get this right here, which we solve / simplify to x equals 3 over 2, aka 1.5.
At this point, you should be comfortable with the concepts, but in math, the best way to find out if you know something is to try and do it yourself. You should be able to do the first 3 problems here. If not, don't worry. Take your time, follow the steps, and see the solution so you know where you got stuck. The last one has 3 equations and 3 unknowns. Using the step-by-step method, it should not be very hard if you think about it a little. But if you can't figure it out, don't worry. Pause the video now and see if you can find at least 3 of the 4 solutions to these 4 problems. Did you find all 4 solutions? If so, congrats! You understand how to solve systems of equations and should breeze through the final part of this video on practical applications. If you got 3 out of 4, you have a solid understanding that will keep getting better as you practice more. Mastery is closer than you think. If you struggled, it is worth it to make sure you understand how to do these problems. If necessary, go back. There's no shame in not getting things right the first time, as long as you get them right the final time, and by the end, understand the concept. Now that we've seen how to solve systems of equations similar to those that might be asked as an SAT question, let's look at some practical applications. If you were to continue your mathematical endeavors until reaching pre-calculus or calculus, you will find an extremely important topic, which is continuity. In calculus, certain rules only apply to a function if it is continuous and if its derivative, written dy over dx, is also continuous. Here, we want y when x equals 2 to be the same regardless of which of the 2 equations you choose. And you also want dy over dx to be equal at x equals 2 regardless of which equation is chosen. Feel free to pause and try to solve the problem. Otherwise, let's get started. Introductory physics is probably the field with the most systems of equations. So let's look at this kinematics problem. Like before, feel free to pause and try to solve the problem. Otherwise, let's get started. A lot of the time in applied math, physics, and engineering, the hard part is finding the equations to solve. In this example, the hard part is figuring out what the two equations really are. Like before, feel free to pause and try to solve the problem. Otherwise, let's get started. Stuff doesn't even have to be moving for physics to use systems of equations. Test your problem-solving skills in the world of statics. Like before, feel free to pause to try and solve the problem. Otherwise, let's get started. This example is one I like because I don't give you the equations. Instead, I give you a silly little word problem. Pause, read it, and see if you can solve it. I really want you to try this one. I will give you a hint. There are only two equations and two unknowns. Pause, and once you're done, let's get started. Let's recap what we've learned in this video. We reviewed what an equation is and how to solve an equation to find the value of an unknown. Then, we have learned what a system of equations is and how to solve it using substitution. We then looked at SAT-like examples as well as practical applications in the realms of calculus, physics, and word problems. Hope this helped!